You've seen this happen, right? A straw in a glass of water looks like it's broken. You see a rainbow pop out of a piece of glass. Well, that's not magic. It's physics. And today, we're going to pull back the curtain on the one principle that makes it all happen, the refraction of light. So, let's get into it.
So here's what we're going to cover today. First, we'll look at the bending light phenomenon, what it actually looks like in the real world. Then we'll dive into the numbers and how to measure the bend. After that, we'll explore a really cool concept, trapping light with something called total reflection. And then we'll see how we use all this to make lenses. And finally, we'll put you to the test to see what you've learned.
All right, let's kick things off with the fun stuff. I'm talking about the optical illusions you've probably seen a million times without even realizing you're watching some pretty amazing physics at work.
Just take a look at these. You know how a straw in a glass of water looks like it's been snapped in half right where it hits the water? Or how a simple glass prism can take plain old white light and just explode it into a full-blown rainbow? Or even when you look at a fish in a pond and it seems way closer to the surface than it actually is. That's all just light playing tricks on your eyes.
So what's the deal here? You've got a bent straw, a rainbow, a fish that's not where you think it is. What's the one thing that connects all of these weird, fascinating visual quirks? What's the secret sauce?
Well, the answer is one single word: refraction. And this is the key. Refraction is just a fancy science term for what happens when light bends as it goes from one material or medium into another one. Think of light traveling through the air and then hitting a pool of water, or going from air into a piece of glass. That little change of direction is what's behind all of those illusions.
And this is where physics gets really cool. This bending, it isn't random. Not at all. It's predictable, it's mathematical, and it's all governed by some really elegant rules. So let's look at how we can actually measure and predict exactly how much that light is going to bend.
Okay, it all starts with this idea that light changes speed. You see, light is fastest in a total vacuum. That's its absolute speed limit, which we call c. But the second it enters any other material, like water or glass, it slows down. So this index of refraction, which we use the letter n for, is just a number that tells us exactly how much it slows down. The higher the n value, the slower light travels in that material, and the more it's going to bend.
Now check out these numbers. It really puts it into perspective. A vacuum, by definition, has an index of exactly 1. Air is super close to that. But then look at water. It jumps to 1.33. Glass is around 1.5. And then you get to diamond, with a massive index of 2.42. That incredible power to slow down and bend light so dramatically is exactly what gives a diamond that famous sparkle. So we know why light bends. It's because it's changing speed. But the next big question is, can we predict the exact angle of that bend? You bet we can. And to do that, we use a fantastic little piece of physics called Snell's law.
And there it is. Now, don't let the symbols and the sine functions scare you off. It's actually really elegant. N1 and theta1 are the index and the angle for the first material where the light is coming from. And N2 and theta2 are the index and the new angle in the second material. That's it. This one beautiful equation ties it all together.
And these diagrams show it perfectly. See that dotted line? Physicists call that the normal. Just think of it as a reference line that's perfectly perpendicular to the surface. It helps us measure our angles. So on the left, light goes from air into water, from a less dense to a more dense medium. See how it bends toward the normal? And on the right, it's the opposite. Going from water back to air, it bends away from the normal. That's the rule, every single time.
Okay, so we know how light bends. Now let's take this idea and push it to its absolute limit. What happens if light, trying to get out of a dense medium, bends so much that it actually can't escape? This leads to a truly amazing phenomenon, and it's basically how the modern internet works. It's called total internal reflection, and it's an incredible trick of physics. Instead of the light passing through the boundary and bending, it hits that boundary and acts like it's a perfect mirror. It just reflects completely back into the material it came from. The light is literally trapped inside.
But this light-trapping magic doesn't just happen whenever. There are two very specific conditions that have to be met. First, the light absolutely must be going from a more dense material to a less dense one. So think glass to air, not the other way around. And second, it has to hit that boundary at a pretty steep angle, an angle that's bigger than something we call the critical angle.
So what is this critical angle? Think of it like a tipping point. It is the one exact specific angle where the light bends so much that it just skims right along the surface at a perfect 90 degrees. Go one tiny fraction of a degree steeper than that angle, and bam, total internal reflection. All the light gets bounced right back inside.
Okay, so we can bend light, and we can even trap it. So what's the next step? Well, how about we control that bending to do useful things for us? And that brings us to maybe one of the most important applications of refraction ever: lenses.
So you've basically got two main families of lenses. First, you have converging lenses. These are the ones that are fatter in the middle. They grab parallel rays of light and bend them all inward so they meet at a single point. Then you have diverging lenses. They're thinner in the middle, and they do the exact opposite. They take those parallel rays and make them spread out, as if they're coming from a point behind the lens.
Now, to figure out exactly what an image will look like through a lens, physicists have this awesome little graphical trick called ray tracing. And it all boils down to these three simple, super predictable rules. If you can just draw two of these three rays, you can predict exactly where an image is going to show up, how big it'll be, and if it'll be upside down or right side up. It's like a cheat code for optics.
All right, theory's great, but physics is a hands-on sport. You've seen the concepts, you've seen the formulas, now it's your turn. Time to put these ideas into practice and solve a couple of problems.
Okay, here's your first challenge. You've got light going from air, where n is about 1, into a new material where n is 1.44. First up, which way does it bend, toward or away from the normal? And second, if that light hits at a 22-degree angle, what's the new angle after it bends? All right, go ahead and hit pause, grab a calculator, and work it out. Okay, you ready? For part A, since the new material is denser, 1.44 is bigger than 1.00, the light has to bend towards the normal. That's the rule. And for part B, if you plug those numbers into Snell's law and solve for that second angle, you get a nice, clean 15 degrees. If you got that, fantastic job.
Ready for round two? This one's a bit of a curveball. We have light trying to get from inside a diamond into water. Your mission is to find the critical angle at that boundary. Remember what that means? It's the point of no return angle before all that light gets trapped inside the diamond as total internal reflection.
So how do we solve this? Well, we start with our old friend Snell's law. The key insight is knowing that at the critical angle, which is our angle of incidence, θ1, the angle of refraction, θ2, is exactly 90 degrees. Once you know that, you can rearrange the formula to solve for the critical angle. You plug in the numbers for water and diamond, do the math, and you get a critical angle of about 33.3 degrees. And to wrap up, I'll leave you with a final puzzle to chew on. Think about a really hot day when you look down a long road and see what looks like a shimmering puddle of water. That's a mirage. Now that you know all about refraction and total internal reflection, can you figure out how it works? It's the same physics we just talked about, just playing out in the air itself. Something to think about.